I am LMU's graduate program recruiter. So I do recruit for all of LMU's graduate programs. I do specifically work with our Seaver College of Science and Engineering students with everything from recruitment to going through the admissions process. And today we have our wonderful electrical engineering professor, Dr. Asghari, with us. So I'm going to go ahead and kick it off with some questions for him. And then at the end, there'll be time for you all to ask questions. And feel free to unmute yourself or type in the chat, turn on your video, whatever you are most comfortable with. Okay, so to get started, Dr. Asghari, do you want to go ahead and start by kind of just telling us about yourself, your academic background, and really what got you interested in engineering and the engineering industry?
Sure. So my name is Hossein Asghari. I have been with LMU since 2015 as a faculty in the Department of Electrical and Computer Engineering. I have been always fascinated since my childhood with astronomy, and then when I got older, I got interested in the engineering. And yeah, since then, when I got introduced to electrical engineering, I was very excited. I thought it resonates with my interest a lot. And then I picked a path of photonics using lights, basically, which was something, related to both astronomy and engineering. And then I have been in both academia and industry for a couple of years. I like both. I like to innovate new things, and I like to see them being used in the industry. So not just publishing paper, I want to see them actually being used. And then I've looked at different applications in the engineering, specifically related to photonics and optics. And my current interest is to do research on applications of optics in biomedical application, biomedical imaging, basically ultra-fast biomedical imaging to detect, for example, cancer cells, or to do something that they do with MRI, but at much faster speeds, basically doing volumetric tissue in real time. And then I have been really fascinated by the quality of students in my lab. Multiple times they have surprised me. They broke a world record multiple times, undergraduate students. And yes, so very excited to be at LMU. Very good students, very good support from the university. I have one of the best lab, I can claim, if not the best lab, one of the best lab in the country, because my supervisors, they were from very big schools like UCLA or Harvard, and they say they don't have some of the stuff that I have. So I have really good equipment in my lab, and I have great students. It allows us to really push the boundaries of science. And then I should be thankful to the university for giving me this opportunity. And then, yes, I'm very excited to be here with you guys.
Wonderful. Thank you for all that. I do know you have a presentation, so I didn't know if you want to go ahead and share that with everyone and go through that now. That would be wonderful.
Sure. I think, yeah, that would be great. Yes, because in the presentation, actually, I wanted to talk about different, perspectives, about myself. Do you see my screen?
Yes.
Okay, perfect. So yeah, I wanted to put a picture of LMU in case there are incoming students. I wanted, if they are accepted or are going to come, I want to welcome them first. It's a great school, great campus, great facilities, and then great basically support. So yeah, so these are my contact information. I shared my slides on the chat. So if you like to look at my slides, you are welcome to check them. So a little bit about myself, personality. Basically, I have a 2.5-year-old son, which goes to LME daycare. His name is Madiar. It's here. I really love coffee. I don't want to say addicted, but I do drink coffee a lot. I like it. I'm good at table tennis. I hope LMU puts a table tennis in the Seaver or some in Dulan so you could play more. I like stargazing. This is the picture I took in the Death Valley one night, and yeah, it was amazing experience, like stargazing. I love traveling. These are the places that I did a 21-day road trip in the west of US. You can see the passes we took. So we went and saw many national basically parks. Very happy I did that. And this picture is from Glacier National Park that we visited a couple of years ago. I really like that. I miss it because of pandemic. We couldn't go very different places, and I hope the pandemic goes down and we can get there. Okay, so that's about me in person. And then about me in academia, I have my bachelor degree in electronics, and then my master degree in telecommunications, and my PhD in photonics. I did a couple of years of postdoc at UCLA. I have been in 2 companies in the industry since then on the side. And then I have been with basically LMU since 2015 as a faculty. I have 14 international and US patents. I have written a book in 2012, and I have close to 100 publications. So I'm very active also in the research. About my research interest, it has been changed over time in different directions in the industry and academia. My current interest is basically help humanity with the power of photonics to do real-time biomedical imaging, for example, cancer cell detection, ultrafast microscopy, and these kind of things. If you like, you can go visit my LMU website, learn more about my research. So yeah, so before I wanted to tell a little bit about my research, and then I can, at any point, if you had any question, kind of stop me. It's a free session. You don't need to wait until the end because you might forget and I might forget. So yeah, if you had any questions, stop me. I can explain more on the topic if you are interested in that topic. So I wanted to say why photonics, right? So why? So there are many fields in electrical. Why I chose photonics? So one of the reasons that photonics is interesting is the speed of telecom. Now you can see that if you say everyone, do you want faster internet? They say yes. Do you want to watch multiple channels on Netflix? Yes, I want that, right? I want to watch cables and have fast internet, and I want to do WhatsApp, video calling in without, blurry. Yes, I want that. So yeah, so the speed of telecom using in conventional electronic circuits is limited, as it is shown here. There are hard limits in the speed of electronics, but photonics, because basically the frequency is much higher, right? So imagine that if the frequency of the wireless communication is like gigahertz 10 to 9, speed of optics is 10 to 12, it's 1,000 times faster. The frequency is 1,000 times faster. So we can send more information, right? So, and that's one of the advantages of using photonics. Another reason to look into photonics is speed of computing. Everybody wants to compute faster, right? So always want to have more real-time things. When you press something, you want it not to wait a couple of seconds, right? So to show you what we can do with power of processing, I show you this graph. So this shows if you spend $1,000 on the computer, how good that computer can be, right? So currently, you see in 2020 is around here. So a couple of years ago, 1,000 computer had the power of insect brain. And then maybe a couple of years ago also had, you see, mouse brain. So they estimate maybe in 10 years, the power of computing with $1,000 is going to be close to one human brain. And then they estimate by like 2050, they are going to basically $1,000 computer is going to have power of all the human combined. You see, but how do we get there? You see that the speed of progress has been slowed down because the speed of computing is limited if you just use electronics. So there's a lot of novel technologies in photonics that allows us to basically push this limit of computing to much faster speeds. Now I'm going to show you basically today a couple of examples that you might like them. So these are the two that I thought you could resonate with, and there are of course many other ones, but I thought these two should be interesting. So, okay, so a little bit about my research. This is what I did in my master's degree. So if you have seen these antennas on the street, they use multiple antennas for the mobile phones, so to increase the sensitivity of the detection. So what I did is that at that time, I had the idea of using lasers to communicate in free space between buildings to have fast internet. And then they had to do something called space-time coding related to this. And then I solved that problem. It was an basically problem at that time. And then at that time, it was not very well received because many people say this is not working and there's a lot of issues with it. But this was in 2006, imagine. But interestingly, in 2015, 9 years later, I saw that NASA is actually using free space optical communication to communicate with Earth. And the receiver is actually in Los Angeles on the top of Mount Wilson. Interestingly, I saw that after like 9 years, people actually use this technology. So it was very interesting. So yeah, so and then NASA is also using this for deep space communication, using laser for that. So has interesting applications. So that was my master's degree. In my PhD, I tried to develop fast computing platforms, for example. So conventional RAMs, that is the memory units that we use in the computer, the speeds are like a couple of gigahertz, like 4 gigahertz or maximum 5 gigahertz. I developed a photonic-based method memory unit, a RAM, that can have huge speed, 780 gigahertz. It was the basically world record at that time. It's just using light, basically storing light instead of storing electronics. The way that we did it, we used basically, imagine I designed this optical fiber Bragg grating. Imagine I have a fiber and design the inside structure in it that allows us to basically store light, trap the light and use it as a storage unit. Also use similar technology to make fast processing platform. For example, Hilbert transformer, which is used is a mathematical transformation that needs to be done in telecom with very high speeds. And also we make like an analog computer using an optical analog computer, all optical. Imagine this calculator doesn't use any electron, all optical at the speed of 1 terahertz, 1000 gigahertz, like huge speeds. And then, yeah, I had a lot of fun. And then at the end, what happened is that these are so fast that there was no technique to capture them. So then I said, okay, I need to develop a method to capture them, which led me to actually develop the first real-time method to capture ultra-fast optical signals in real time, which led to my company actually. I did this experiment in 2009 and it didn't exist. And I thought, okay, I want to see this in the market. And it took me maybe like 10 years. And then I could put it to the market. So I made a spectrometer, which is like a capturing device, which operated at 1 billion frames per second, huge. It has very different applications. And then after that, I got interested actually in this technology, ultra fast detection. And then I went through different passes, as you can see, telecom, medicine, scientific research. And then at the end, currently I'm focusing on medicine. But let me show you some examples. For example, for the first time, I could show the birth of a laser. Before this capturing, this is actually the first time that ever anybody has shown the birth of a laser, because lasers are very fast. Nobody had seen a burst of laser. And what you see in this picture, this is the evolution of the spectrum, the frequencies from noise, this is noise, to this is got basically a burst, a basically explosion of energy, which leads to mode liking, which is the burst of a laser. I showed this in 2015 in an exhibition in Photonics in San Francisco, and was very exciting to see the eyes of really the CEOs of companies seeing this for the first time. Another application that I use this basically fast detection technology is to develop fast cameras, right? So in many basically issues in diseases in medicine, the number of basically cells that are disordered are very small. So I'm putting, for example, if they're circulating tumor cells, like 10 out of, like, imagine 5 trillion or 5 trillion, yes, cells, right? They are so small. It's like finding a needle in a haystack, right? There are so many, especially if you want to detect them in early stages, right? So then if you want to use normal capturing methods, cameras to capture them, it will take you forever to find this, right? But using this technology, we developed a camera, right? A camera that was the fastest continuously running camera. We had our optics, we had optical amplifiers, we had FPGA boards like back-end electronics that could capture them in real time. And this is basically a close-up of where the cells could pass through, and our camera is in the back of it. You could capture this in real time. And this shows basically an example. So imagine if you use just normal CCD camera, when there is no flow, of course you get very sharp images. But when the flow of the cells becomes very fast, here 4 meters per second is really fast. And you can see even with the CMOS camera, it has a shutter speed of 1 microsecond, is 10 to minus 6. Still you see blurry, right? You see blurry. But with our method, because shutter speed is so small, even at 4 meters per second, we get sharp images. And this way we can have a high throughput of looking at all the cells in real time. Here I have a cool experiment. Okay, so we were working on this stuff. And then one day I was working with my colleague. And then we were trying to capture some images, and his son was playing guitar in another room. And I saw when the person is playing guitar in another room, I'm picking it up from my system. Imagine how much is the vibration. Somebody playing guitar in another room, and you pick it up here. And it was really amazing. I have this video that maybe I can show you. Can see the setup and see that actually we captured this on video. So you see that the mirror is on that basically a speaker. And then in this experiment, this is our setup. We have a software, and then this is our system. This is the oscilloscope showing these fringes. And then you see my friend just blowing air. You see, it's blowing air, how much the thing moves, right? It's like nothing, right? But here, as soon as he blows, you can see the movement. See, it moves very fast. You could see the smallest movements. And actually, this is an active research currently in my lab. We think we can break the world record in terms of sensitivity with this technique. So basically, yeah, so this technique has been used to make a very fast camera, 4 trillion frames per second, just so fast the light freezes, so fast that if I take 2-hour movie with my camera and you want to watch it at 30 frames per second, it will take you 30 million years to watch that, right? It's huge, right? So yeah, this is also, we have this at LMU, so you could come take a look. So yeah, so then I got to look, now I capture these things, now I get to the big data problem, just so much information coming to my system. How can I basically solve that? Then I got to, okay, how can I basically compress the data, not on the computer, because the optical data is just so fast, computer cannot process that in real time to compress it. Then I thought, okay, the nature has solved this problem for me a million years ago. How? So basically the amount of information going to our eye is just so much. If you wanted to see everything in real time, we would not be able to see in real time if we didn't have this technology embedded in our eye. What is that technology? The back of our retina is warped, actually. The image in back of our retina is warped. This shows the concentration of the basically sensors. Vision sensors in the back of retina. You see there is a huge concentration in fovea, and the rest it warps, right? So the image in our eye is actually warped, and based on this, it can just select the right amount of information to compress it in real time. So I developed this technology, and we patented this technology, something that uses basically light to compress the data. So here you can see our comparison to JPEG. This is JPEG is 56 times compression. This is our method. You see, it has much better compression. And it got all over. Many news agencies, they covered it. We went to the basic cover of big magazines. They called it putting the squid on big data. They called it anamorphic stretch transform. What's great. And then another thing we did is that we found the similar technology can be used to find edges. For the first time, we've developed a technology that allows us to see the edges of images. And of course, because I was interested in astronomy, I applied it to astronomy, the first thing I did. So I show you this interesting image. This is the picture of Uranus, right? And you don't see much on it, right? It looks like a bluish, right? But imagine after my technique, you see now you can see these patterns on it, right? You can see hurricanes that you could not see with naked eye. And then I saw that the NASA actually sent another spaceship to take another picture. There's another picture taken like 15 years from the first one. And when I applied mine, I see similar pattern, actually just rotated. That shows we can use this for many technologies. I applied this, you can see this is original image, this is after my technique. I applied to biomedical. We developed the software that basically doctors could go through the brain in basically layers and they could see the features of the brain in real time. And then, yes, so that was what I did in my postdoc and PhD. Okay, so what I'm doing now, my current focus is on high-speed biomedical imaging. This is a picture of my lab. There are many students working in my lab. It's an active lab, and we are very fortunate to have good equipment. Here, I wanted to show you some examples. So, for example, in this experiment, I wanted to capture basically anomalies in the fan, in a fan, right? So, imagine there is basically a fan, there is anomaly in the blade. What was the application? This was the time that, if you remember a couple of years ago, there were multiple planes that they failed because of there was failure in the engine. And then imagine if you had a real-time method that could capture these anomalies in the engine. As soon as it happens, maybe the pilot could save, right? So here, imagine I wanted to simulate that environment. So I created this fan to simulate an engine of a plane. And I created this distortion in one of the blades. And here you can see operating at 400,000 frames per second, this camera, I could see these basically small features. And then I push it, of course, to the limit, right? So I like that. So okay, so now this is captured this blade picture at 100 million frames per second, which was the fastest by that time. This is normal blade. This is with distortion, right? Basically here we have huge 10 to 4 basically captures at this speed, and we could see this basically anomaly. This is imagine capture in 10 nanoseconds. As soon as 10 nanoseconds, you can find there was a problem in the engine and you could tell the pilot about it. Another application that we are working on is called basically OCT, optical coherence tomography. This allows the doctor to see inside of the body, not just the surface. Imagine like MRI, right, that they see, but for MRI, you need to wait 30 minutes for one image. Imagine this is a fast method. It could give you basically volumetric images of the tissue in like millisecond, right? You could operate up to 1,000 volume frames per second. And yes, we had some interesting results. This is an active research. There are multiple projects going on it, and we are very basically happy about our progress. Another project that has been going on is an ongoing project at LMU that I'm working on. It's called non-invasive glucose meter. Multiple groups at LMU students, they have worked on this. So typically, diabetic patients, they need to basically draw blood, and that's painful to pick the finger. So we have a non-invasive glucose meter using light again, using photonics, that doesn't draw any blood. And then it shows promise. So we recently could see clear difference. Of course, we had a great support from LMU. We have like variety of laser. We have a super continuum laser that looks at all the wavelengths. It allows us to explore this, and we have a great spectrometer that allows us to see these long wavelengths. But we could see these patterns, and it's amazing that laser can now be used actually to allow. Basically, I'm envisioning maybe future, maybe Apple Watch or something like that could actually see the amount of glucose in humans in real time, and diabetic patients could benefit from it. Yes, I also teach capstone projects, many interesting projects going on. You have the slide, you can download. There are many of them, they have website. You can check all the websites of our projects since 2015. You can check what they are doing. They're working on really cool projects. Yes, so maybe I can show you a couple of examples of this. Yes, for example, you see, like last year, they were working on making an affordable smart bike. It's less than $200. In another project, we had a student that was a circus basically performer, and he wanted to make the Chinese pole a musical instrument. Amazing, basically idea. As he were dancing around the pole, he was playing basically music with it, right? Another project, we were using brain mapping. Basically, our student developed this technique, this platform that could read basically the waves from the brain. We have a smart car initiative, right? That basically we are trying to make a very, basically a smart car, something like Tesla, right? Our students, they develop different, basically systems that make it smarter and smarter. This is the current platform that we are working on it. Very cool. And many of our students are interested in the music. And this is, for example, they made an affordable modular analog synthesizer. Yeah, so, okay. So yeah, so many projects are going on, a lot of drone projects. Yeah, so yes, maybe I can stop here, and then yes, and if you had any questions about the projects going on or my own research, I'm happy to basically answer those questions now. Yes.
Wonderful. This is amazing. We do have one question in the chat that I wanted to read out. I don't know if you can see while you're sharing your screen.
Oh, yes.
But it was asked, what kind of academic background do you need for this program? They are a final year physics students. And then they asked if this program, Introduction to Photonics Engineering, is in general, or do you need to have that background as well?
That's a good question, actually. So when I came to LMU, I was only in the previous school, I was only working with PhD and postdoc. I did work with undergrad, but not this much. And then I had this, my mind that, yes, can the undergrads do these great things now, you know? But I was really amazed. What our students, they did was amazing. So answering the ways, if I say that correctly, you don't need anything that you need, we teach you in my lab. So actually, I mentioned that my students, they broke the world record. They were first year students. 2 weeks, there was a group of 3, they broke the world record in just 2 weeks. And yes, never underestimate undergrad. They have really sharp minds. And because they don't have bias in their brain about what is possible and what not, they can do amazing things, you know. So I think we do have a couple of, some of the students are working with me now in the chat in here. But yeah, so typically when basically a student come to my lab, their knowledge is limited, but they typically work with other students and me. I basically train them, you know, to work with basically you know, these techniques. I give them the right background, I give them papers to read, and whatever they need, I teach them. And then, yes, they don't need any particular background. So the student in my lab, some of them are electrical, some of them even are mechanical, you know, because there is in my lab, there is an overlap of both of these basically disciplines, and they work very great because they need basically design some mechanical parts. Some of them are the signal processing, all of them are needed. But not particular background is needed, you know. At any point that they have knowledge, we could use that, you know, and then build upon that, you know, to get to the next step.
Wonderful. Then he asked if you do any quantum research, quantum computing as well in regards to photonic technologies.
Sure. Yep. Yes. So yes, the photonics now, they are basically going hand in hand with quantum, you know. Basically, there are many topics in quantum that overlaps with photonics. we do use them, but the way that I look at them is system level. What I mean is that basically you could be a physicist, you could take a look to, yes, this is quantum, this is entanglement, how can I use it, where can be used? But engineers are not just physicists. We use physics and math to apply them to something, right? So quantum entanglement, all of these, they do exist in many of the technologies that actually I mentioned. For example, ROGWAVEs, optical ROGWAVEs, we discovered it for the first time, which is development from quantum actually. But what we do, we use the applications of quantum. Where can we use them? Not just understanding them, where we can use them, because we are engineers, And then my background was electrical. When I reached out to photonics. Photonics is something between engineering and physics, but I look at the photonics from basically applications perspective. We don't go that much to the details of what is the quantum part, but we use applications of that, where we can use it in applications.
Wonderful. And then it was asked about the dual degree program. So yes, any of our Seaver College of Science and Engineering graduate programs can be combined with our MBA program. So that is an option for students who are interested in getting both degrees. You first apply to the Seaver program of your interests, and then once you are in the program, you will transition to the MBA program once you meet with an MBA advisor. And then they asked about scholarships available. So we have a lot of different versions to get scholarships and financial aid. So we see our students who are coming to LMU get things such as research assistantships and graduate assistantships, which is working on campus, working in research, or working in an office. And you can receive obviously financial assistance through that. The Seaver College of Science and Engineering has a departmental scholarship that our students are allowed to apply for. And then there are also need-based aid applications that you can apply for through our financial aid office. So then we have another question that says, what data set were you working with when you analyzed the Saturn picture? Was it just a regular image, or was there additional data that you had access from NASA?
So NASA, and thank you for the question. So yeah, some of the pictures on NASA that are publicly available. So I've used the publicly available data sets from NASA in this picture, and then also this picture. There are other pictures that I'm not showing here, but yeah. So if you're interested in this method, there is a Wikipedia on these techniques now, and the technique I developed is called. If you search on Wikipedia for phase stretch transform, it brings my method. And then we have a code on GitHub, is publicly available. You could run basically this edge detection method. You could do it yourself and test the method. I typically at that time, whenever, for example, the Mars rover was taking pictures, I would apply it. And I found that sometimes they modify images, you could pick it up because it shows you when they modify, a human cannot see that all changes, but my method could see the differences, those edges, and yes, so it's a cool method. I suggest if you're really interested, you could test it, this stuff.
That's wonderful. So Yanette just posted the curriculum for the program in the chat. So I know it was asked the core modules are for the program, kind of what the courses are. So that link there will take you to the courses on our website. Dr. Asghari, I don't know if you want to mention anything about the courses our students take in the graduate program, or what you see students take.
Sure. So yeah, for basically there are some 500 level course and 600 level course, which basically seniors or graduates they could take, like if they want to continue the path in optics, they could take these courses. Of course, there are lower division courses in optics as well. But the students that they come to my lab, basically they learn these things. They don't need to wait for that course, they learn everything basically firsthand, doing the experiments actually. But yes, if some of the students that I had, for example, I had a graduate student, he was working at Northrop Grumman, at that time. Actually was a software engineer, but he really liked optics. He never had a chance. And he took my course, and now he's very happy. He's an optical engineer at HRL in Malibu. So yeah, so I have seen people, you know, that they find their path. Sometimes you work with something and you resonate, you know, with that. So optics might be that, you know, you could try it, and you might find that this is really something I really like to, you know, learn more and work on it, you know. Yeah. So some students also have taken this course as independent studies. They could take this course earlier. Mm-hmm.
Wonderful. Do we have any other questions? Feel free to put them in the chat or unmute yourself, whatever you are comfortable doing.
Yeah, I put my contact information in the basically in the slides. If you like, you could always reach out to me, and then I could tell you more. There is a question: what industry links do university has? Yeah, so apparently we have good. I think maybe Emily could also tell you more about this. But from my side, I can say that we have many alumni, you know, working in the industry. Let me see if I can show you basically this is the companies that our alumni are working on. You see, all the good companies, we have alumni in SpaceX, Raytheon, everywhere. And one of my actually this year is getting to NASA. So we have alumni everywhere. We have good contacts. And then many of our students, they get really good internships. They just leads them to basically great jobs. But I suggest LMU has a great, basically, I think, I don't know what the name of that program that helps the students to find basically internships and jobs. So maybe Emily can explain those better than me.
Yeah, definitely. We have a wonderful career and professional development office that has like industry specific career coaches. So we have a career coach that just works with the Seaver College of Science and Engineering. So they have connections at, you know, all of the companies in the LA area. And our career coaches help you with everything from finding internships, finding job opportunities, connecting you with alumni. They also will help you with things such as, so say you got a job offer, they will help you look over your job offer, negotiate the pay of it. They're really just trying to prepare you for the real world or for a career change or a job change. The Career and Professional Development Office also puts on career fairs throughout the year and different industry events that will help connect you to different companies and also just connections in the area. And I'd say our Seaver faculty themselves have, as you've just heard, have extremely impressive backgrounds and have a lot of connections themselves. So the more you connect with faculty and staff at LMU, the more you you will become connected to different industry professionals outside of LMU. Do you have any other questions? Okay, well, if you don't have any other questions, we really appreciate you all coming. I'm going to go ahead and put in the chat the graduate admissions email. So if you have any questions after this for the admissions team or for Dr. Asghari, we will forward the email to him. So feel free to reach out to us, stay in contact with us. If you have any questions, we're all here to help you. But we really do appreciate you coming today and hearing about LMU.
Great. Nice to see and meet everyone. Have a great evening. Bye.